Matteo, can you double check that we are live?
Yep, let me check out this, see. And yes, I see it. Cool. Awesome. Antoine, are you ready?
Yeah, let's do it. Thank you so much for the invitation.
Amazing. No, thanks so much for coming. So yeah,
No,
let's take it away.
for sure. Today we're gonna speak about elephants, which is always exciting. I'm presenting a project on behalf of Vaibhav, who's on the call today, Tim, and our PIs were Elizabeth Bondi-Kelly from University of Michigan, and Sarah Berry, who's my professor at MIT. And this talk is gonna, like, my project is interdisciplinary. I'm working in between interpretable deep learning and ecology. So it's always a bit hard to try to connect both. So if you have any questions, feel free to ask me anything. I will try. I guess most of you know a lot about interpretable deep learning, so I'll try to give you some ecological insights. But yeah, the talks are always a bit hard to adapt to everyone, so feel free to ask anything. Just a quick word by myself. So I'm a first-year student at MIT, and I work in interpretable computer vision. Our lab is dedicated to building models to better understand ecosystems and build representations of ecosystem in a deep learning with a focus on computer vision. I also have a YouTube channel where I speak about science communication. It's called Antoine vs. Science. Please subscribe. And I host a adventure show on the national television in Switzerland. So I'm very much into science communication and documentary filmmaking and stuff like this. And actually, I have, like, my hard skills are in deep learning, but my true passion is ecosystems and biodiversity, which I grew through making documentaries. So this project allows me to connect a bit both worlds, and especially I work on the problem of elephant re-identification. So as you may know, elephants are very much in danger. The main cause of danger is poaching of their tusks. Still today, they are being hunted for their tusks. And in the last 50 years, we lost 70%, 77% of the population of African elephants. Actually, we can divide, like 2 years ago, we realized that there are two different species of African elephants, African forest elephants and African savanna elephants. And African savanna elephants lost actually almost 90% of their population in 50 years. So it's really bad. And there's a huge problem to try to figure out ways to ensure their conservations in Africa. Especially conservation relies a lot on the problem of re-identification. So re-identification is being able to find the identity of a single elephant, like literally the name of the elephant. And it's a very hard problem. For example, you have reserves like the Kruger National Park in South Africa, where there are about 20,000 elephants. And we think there are 20,000 of them because we cannot re-identify them. There is not a list somewhere with all of the identities of the elephants. And it's a very hard problem both for AI and for humans. And basically both AI models and humans are failing at re-identifying them. There are methods. They are very heavy on the time it takes for the experts, but there's a big drive to identify them. And especially it's important if you want to estimate their populations, because basically you don't want to count them twice, right? There are models of abundance and demography that can be based on some uncertainty of re-identification, but basically we can divide the uncertainty by 10 if we actually are able to re-identify them. It's also important if you want to study their behaviors, you want to see them across their lifespan and see how their behaviors evolve, if they are socializing with different animals. For example, the nonprofit we collaborate with was able to discover that old males play a very important role in the socialization of young males. And this can only be discovered because you can see an old male repeatedly interact with younger males and stuff like that. So re-identification is both very hard and very important. The problem is what I just defined. You have a gallery, a list of all of the elephants you know. You have just images for them. And when you bring a new image, you have to discover which one is the right elephant. So this is the query here on the right, and you want to link it to one image in the gallery, and then you make the assumption that the identity of the image in the query is the same identity of the image in the gallery. Do you want to try to guess which one in the gallery is this query?
I think it's, yeah, I was
right?
gonna say that.
Yeah, Yeah, it's actually a trap. I used images from the same camera trap, but actually it's the middle one. It's, oh my God, what happens? Oh no, you're right. Oh my
Yeah.
God, I was wrong. No, sorry. Like everyone thinks it's this one, but actually it's that one. It's the different one. So you see that one of the problems is to be able to build these representations that are invariant to pose and luminosity and camera types and stuff like this. So this is a very classical computer vision problem, but we have to apply methods that also come from ecology. The idea is that you want to build functions that are invariant to pose, illumination, background to build a representation. You are all experts in deep learning. You know what I mean here. Okay. So the classical way to do it, you guys know it. This is more for ecologists, but either you use a like classic triplet loss. In our case, we use a more modern atlas. You do metric learning. You try to bring together the representations of elephants that share the same identity and take apart the negatives. I'm not teaching you anything, but here I'm going to teach you something because you're not elephant experts. This, what I'm showing you, is SEEK codes. And this is another representation system that's made by ecologists to try to represent the identity of elephants. And the idea is that it's based on 16 different features on their body. And it's basically biometrics. So you're going to ask 16 different questions. And based on the answer to these questions, you can build a list of answers, and you can build this string of stacks that you can see down to the right. And technically, this string of stacks should be unique for an elephant's identity. So we're going to see how it works. The first question you ask is the sex. Is it a male or female? Does any of you have any idea? Okay, I'll help you. It's actually a male, and you can know it because it has a little hump in the back of their head. So you put a B for bull. We call them bull and cows. It's also an adult, so you put 00. This is for the decade of birth. And then we're going to look at the tusks. So you see the elephant on the right. The right tusk is absent and the left tusk is present. So we're going to encode this in the code. And then where it becomes even more important is for the ears. You're going to look in both ears where are located the biggest tear, the biggest hole, the second biggest tear, and the second biggest hole. And you have a system of localization where you use like the clock system. And for example, if you look on the right ear, where is the most biggest, like the biggest tear? You can see it here. It's like pretty much in the middle of the ear. So you encode this by A8, and then there is no like significantly big holes in the ear. So you put a 0, that means there are no holes. And then the second biggest tear is this one that's a bit lower. So it's a 7 in the system that's established here on the left. And then no smaller holes. And for the left ear, actually, we cannot see it. It's occluded. So we use a identifier, which is the underscore, which basically means I don't have the information. I don't know where it is. And then you have a few more other biometric things that you look where, like, does the elephant have extreme special ear features, and you end up with a full code like this. Technically, this code is supposed to be completely unique to this elephant, although we're going to see that it's not actually perfect. You have a question, Aya?
Yes. So what's human accuracy on this task? Like a random human, non-expert elephant human? This is very hard.
Oh, yeah, it is a very hard question. Actually, so I don't have the exact number, but we're going to see, like we have tried this on data sets that were emerging from volunteers that would try to guess this and realize that actually it was too noisy to get anything from these SEEK codes. And the truth is, actually, if you also train a AI model to try to predict anything only from the SEEK codes, trying to extract the SEEK code from the image and then trying to do the retrieval based on this representation system, it's also too noisy to get anywhere. You're below 1%. So it's very, very true that that humans, like, it's a very hard task. And one of our conclusions is that this should be done by experts, and it's fine because it's usually a task that's done by experts. Also, one of the problems is that this is a pretty low dimensional space. It's a 63 dimensional space because you have 16 questions and each of them have somewhere between 2 to 6 possible answers. So if you encode them as like one hot vectors, actually it gives you vectors of dimension 63. So you have a low dimensional space where you have a big number of images that are encoded. So you really have a geometric problem where if you make an error, you're going to shift very closely, but because the space is like very crowded, very populated, you're very soon going to shift towards another close negative. So yeah, this is a good question. Here actually we don't have so much tolerance for errors, and errors are very common because it's a hot task. And sometimes there's not even a right answer. Like, is it exactly on this corner of the ear or is it more low? Like, it's really up to interpretations. And also you have like occlusions that can cause ambiguities. And this is why actually we decided to start this project where we're going to pair this approach with a deep computer vision approach to try to use the best of both worlds. Yeah, so let me go on. But yeah, one of my key message here is that this SEEK code system is really encapsulating 30 years of like experts being on the field, trying very, very, very hard to identify the elephants. And they came up with the system that like slowly evolved year after years as being the most optimized for the task. So I think there's something really interesting here, especially in our field of interpreted deep learning, where we used to think that, oh my God, like we can use the expertise of models to try to extract something and then build expertise that could be helpful to domain experts. But actually, we can also think the other way around, where we have this like old school expertise in this field. Can we think about a model that infuses this expertise in a deep way? So let's try to see how we do it. The first thing we do is that we know that experts rely a lot on ears for re-identification. Most of these features are related to the ear. So what we're going to start doing is actually just crop the ears. We use just a very standard YOLO on this that's like fine-tuned for this task. I'm in a very funny lab where if you ask one of your lab mates, guys, does anyone have weights for cropping elephant ears? Someone will say yes. And you're like, oh, well, someone has this model. So I could just use my lab mate's model to crop the ears. And we build a representation that's using all of the, like both ears. And where it's interesting is that you see that some of these features are very small. And you need the resolution of the crop to actually be able to see these little tears and these little holes, where if you like preprocess your images to 224 to 224, you might be losing this information. So we take the input, we take the query image, we crop the ears, and then we're going to embed all of these together. And the way we do it is that we embed the whole image, and then we embed each ear, and then we just concatenate together the embeddings to make a like bigger embedding space. You might be making an error because these AI models are only performing. Oh my God, I should have updated my slide. It's actually, they only perform at 19.6%, but it's actually, well, I'll go back to it later. Then what you do is that you try to predict these SEEK codes, these concepts from the image. So we use a pretty classic concept head that's trained with like a cross entropy loss, like multi-class cross entropy. And you try to infer, to predict all of the values of these concepts, like the classic CBM way. And then what we do is that we ask a human to correct these concepts, and then we project these corrections back to the embedding space. So this is the idea. This is what we want to try doing, and we want to hopefully use the human corrections as a way to, like, we want to project them in a deep way and really improve a lot the capability of the model. In a lot of setup, you want to avoid asking humans for corrections because it's annoying, it takes time, experts have limited resources. But here, this problem is so hard, either for humans and for AI, that it's actually okay to ask humans to spend some time on it, because if they don't spend any time on it, there's just no solution at all. So it's like we're solving a problem, hopefully, that there was no solution for before. So it's fine if it's not fully optimized, fully automatic. Okay. So yeah, this is the theory. We take the image, we encode it, we extract the SEEK codes, we correct the SEEK codes, and then we project a correction in the deep way. The dataset we work with is a dataset that comes from the Masai Mara Natural Reserve in Kenya. It's a dataset that contains about 70,000 images for about 1,000 identities. What we do is that we split the gallery and the query in a way that we make sure that for each query, there's always an elephant in the gallery. The idea is that like every query should be possible to be linked to somewhere. So we're really working on a closed set retrieval problem. We don't accept new elephants in the gallery. We wanted to keep it easy in the beginning to try to have a proof of concept, and we'll try to open it later for actual deployment. You have a question? It is not consistent with UG specific.
I'm answering in the background.
Oh yeah, sorry, I didn't see the message. Sorry. Yeah. So we split also the gallery and the query such that the different encounters, so like the setups in which the photos are taken, are never split across the query and the gallery. So very often when they see a group of elephants, they're going to take 100 pictures, sometimes 20 pictures of the same elephant, and the background is going to look very similar, the luminosity is going to look very similar. So we make sure that these encounters are always split across the gallery and the query, so that this information cannot be used by the model to retrieve the identity. Okay, so let's go to the actual architecture, what we do. This architecture comes from Vaibhav. He came up he came up with this a few years ago with Sarah and Liz, and the initial name is called Chair. So what we do is that first we embed, sorry, oh my god, sorry. We embed separately the body, the left ear, the right ear. We concatenate everything, and then when we do a simple KNN retrieval benchmark on this, we end up with 19.6% here. But actually, this 19.6% is a pretty good value, because if you compare to more naive approaches where you would use a model that only works on the whole image, you're always below 1%. So we see that we have a huge, no, actually we have 1.9% if you fine-tune mega descriptor. So actually you realize that you have a huge improvement that just comes from the idea of cropping the ears and getting these fine details in the ear. The models we use is mega descriptor. We also compare it with MuID. It's actually a swim transformer that's been pre-trained on a lot of ecological data. It comes from a postdoc in our lab too, and it shows usually it's a model that's pre-trained for re-identification of many different species, and it usually shows good performance for this task. But we, like as I said, like basically elephant look a lot alike, and it's a very hard task even if you fine-tune that kind of model. So we need to come up with like a custom architecture for this problem. Okay, do any of you have any question? And then we can, before I move on. No? Okay. Okay, so this is like the very classic computer vision deep learning baseline. Here we extract the concepts. We use the same architecture. We just probe it to extract the different values for the concepts. And we see that when you train the concept head with a traditional cross entropy, you can predict very well the age, you can predict very well the sex, but all the tasks are very easy to predict. Some stuff on the ears is much harder to predict because these are details, and often there's like some kind of like geometric grounding where they need to know, oh, where is it the most prominent hole, is it the second most prominent hole? But overall, like the best result of our ablation is 83.9%, which is not perfect, but which we consider enough to move on with. But there's a very annoying detail. Okay, this is the most boring slide of my presentation. There's a very boring thing about these elephants, which is that you have the data set we have gives us SEEK codes, these concepts for each sighting, each encounter. And the problem we have is that on some of the images of this sighting, you're not going to see one of the ears. So you're not able to actually predict the values that are contained in the labels. So what we do is that we use, once again, our ear detector to mask the SEEK codes accordingly. The problem is that we end up with actually two different labels for each image. We have the sighting level SEEK codes and the image level SEEK code. The idea is the sighting level SEEK code contains all of the information that you would get if you have access to all of the all of the images in this sighting, while the image level SEEK code is only the information you can access by looking at this image. It's going to be a bit confusing because across the whole presentation, we jump from like sighting level to image level corrections, where you sometimes use one, sometimes use the other. So I'm very sorry if it's a bit confusing in the rest. If there's something that you need to remember, it's that the sighting level SEEK codes contain more information than what can often be extracted just from the image. So there's like a little bit of cheating actually when you use sighting level correction, so, which is why we often try not to do it when the elephant is not re-identified yet. So in your gallery, you know the identities of your elephants already. So you can assume that you can do an aggregation, and then you can aggregate the SEEK codes to come up with the sighting level SEEK codes. But at query time, if you have just one image, you cannot see what's on the other side, right? So using the sighting level SEEK codes would be cheating for evaluation. So we tried like not to do it. Okay, let's move on. Okay, yeah, this is what I just said. Okay, first we extract the embedding. Second, we extract the SEEK codes, and we see that if you just try to do KNN on these SEEK codes, this is really bad. You can't do anything. But then you can ask a human to correct these SEEK codes and to spend some time on the image, and we can try to see how much do you perform using these corrected SEEK codes. So based on the number of correction you apply, whether you correct 0% of the images, 50% of the images, 100% of the images, you can try to see the different performance. So you see here, if you correct with sighting information 100% of the time, you could potentially go all the way up to 82%. But once again, this is considered cheating. So actually here, the most realistic baseline is the last row and the penultimate column. It's 48.6%. This is like the realistic baseline for SEEK code retrieval only. So only in this like low dimensional space. Then, yeah, okay, I'll move on this. Then we do what we planned. So we project back this low dimensional SEEK code to the high dimensional space, and we make a weighted sum between the original embedding and the projected concept. The idea is that you kind of have a skip connection between the deep thing and what emerges from the concepts, and we try to sum them as a way to fuse the information in a edited embedding space. And the question now is to evaluate the model. How well do we do if we use these edited embeddings? And we see here that the fusion parameter, the fusion weight, is called alpha, and we'll see later that actually we can either put it fixed to a value of 0.5, or we can decide to treat it as a learnable parameter that's trained like a concept weight. Okay, so these are the performance you obtain when you evaluate this architecture. On the left here, you don't correct anything. So this is the pure, like if you just let it use, yeah, thank you very much. No correction, you just automatically use it, and we reach about 20%, which is similar to what a traditional computer vision thing would do if you use the ear the way we propose. We actually do slightly better than just using the ears, which is an interesting detail, because that means that even if you don't bring any additional human supervision, you still have a little gain in performance. And this makes us believe that what we have here is not just a way to inject more human supervision for a retrieval problem, but it's also a way to design a bias that's actually corresponding to the problem. Maybe the SEEK code approach is a good way to think about the problem that ecologists invented over 30 years. And when you force the model to think like this, you have a little gain in performance without any correction. And then we see that when you go on the right and you add more and more supervision, more and more correction in this concept space, then you gain in performance, and you can reach levels that couldn't be reached by using only SEEK codes or by using only a single non-interpretable AI method. So I like this because I feel like back in the days when I was learning about the interpretable AI doing my master thesis, people were always telling us that there's a trade-off between interpretability and accuracy. And here we observe the opposite. If you actually use concepts that emerge from a domain expertise, we actually do better, even without correction. So that's exciting. We compare it with another elephant retrieval method that was used before. We do better than them, and in addition to doing better, we also have a higher slope, which let us believe that our method, the way of summing the two things, is actually a pretty optimized way to fuse both information and to really use the information brought by the supervision. So this is the performance of the model. But here we used diagonal correction. So what I mean when I say that we use diagonal correction, that means that the amount of correction that's applied on the gallery is the exact same of the amount of correction that's applied on the query. Basically, when I say 25%, that means over the list of all of the elephants before, the ecologists will go in their files, correct 25% of them, and whenever they have new pictures, they will correct 25% of the new pictures. But this might not necessarily be the most optimized method. So we try to compare with all correction levels, both on training and inference, so on the gallery and the query. And here it's very interesting. We see that the more top right you go, the higher values you have, which is interesting. We can go all the way up to 89% if you correct everything, which is really cool. Because you do better than SEEK codes, you do better than both AI and SEEK codes, even with full correction. But we see that there is a slight asymmetry here. It seems that correcting at inference time, correcting the queries, seems to have more effect than correcting the gallery. Actually, when you correct more than 20 or 30% of the gallery, sometimes you even have a little decrease in performance. And actually, our hypothesis on this is that when you apply corrections on the gallery, you actually collapse. So before correcting, you're going to make errors. And because there are ambiguities, the geometry, the region where your elephant is going to be present is not one single point in your space, but maybe one here and one there and one there in a little region, such that errors, we actually disperse them a little bit. But when you correct them, you actually collapse all of them to only one point in the space. And because there is ambiguity, and as you said, it's a very hard task, maybe it's better to have some kind of label noising in some way, although it's for concepts. But yeah, so actually correcting below over 20 or 30% might not necessarily a good idea. And experts should put their effort more into correcting the new queries once they have a gallery that's been corrected partially. And you see that here, if you apply maximal correction, we have almost 90%, which is a huge gap compared to what we had before, which was 2% with just a pure AI model. And suddenly we can think about deploying it, and it's actually becoming useful. And the truth actually is that when we started the project with Vaibhav, what was it? It was a year and a half ago, something like this, Vaibhav. We did it out of mostly research curiosity, and we thought that maybe it's interesting, and so it's a good example to demonstrate how some problems can be very hard and you can bring expertise, blah, blah. And actually suddenly we realized that we end up with we have the SEEK codes for all of the elephants, both in the query and the gallery, which is why we can simulate corrections level all the way up to 100%. And actually when we realized that we go all the way up to 89%, we realized that it might actually be useful to the people in the field. So now we're thinking about deploying it in Botswana, in a natural reserve with a nonprofit called Elephant for Africa. Okay, let me move on. Do you have questions?
I actually have one. Just
yeah.
For maybe we're in this stage. When you do the corrections, how do you choose which parts of the code to fix? When you say 25% of the corrections, for example, of the SEEK, does that mean you fix the entire SEEK code, or you fix 25% of the entries of the C code.
Yeah, 25% means that 25% of the C codes are going to completely be corrected. Basically, I assume that if the ecologist is sitting
The whole thing.
in front of the computer, they're going to correct the whole C code while they're looking at the image, which usually takes them about, I'd say somewhere between 2 and 5 minutes to do. It's not a big.
And do you have some intuition as to whether this could be done like with partial corrections? So, for example, just the model give a bit of uncertainty in like which parts of the C code may be need more attention, for example.
Yeah. Actually,
So
it's something that I explore here. So I'll jump here while you're asking this. We try to dissect them to try to see which of the attributes is actually helping the most. So what we do is that we train logistic regressions using either all of the concepts versus all of the concepts minus the concepts we're studying, and we try to see which of the concepts actually bring the additional, like the most additional information for a retrieval. And we see that the ones that help the most are these details on the ears. And I think it's interesting because if you think about the sex, let's say we have half males, half female. If you have the answer, you can only divide them in two, right? But if you have the information that, oh, this is the elephant that has a little hole here, then it brings a lot of discriminational information. And I think there's something really interesting there, especially for all of us who are thinking about concepts and stuff. Like, what is a good concept? And I think what is a good concept really depends if it's like one of the first concepts you have, because the first question you would have is what's the sex, and you can divide them in two, or whether you already have a lot of them, and in a combinatorial way, this concept is going to bring a lot of information. I like to think about this like you remember the game when we were kids called Who's Who, when you have to like flip the faces and you ask questions to your sister, like, does the guy have glasses? Basically, the way to think about it is like, what are the good questions to ask in a Who's Who for elephant, right? And the question depends if you're in the end of the game or in the beginning of it. But I'll get back to it, because actually one of the things let me get back to this. You remember the alpha parameter? When you turn alpha parameter into a trainable parameter, you actually realize that the more correction you apply in the gallery when you train the model, the more the model is going to learn to rely on the concept branch rather than on the visual branch. So this is like what is expected, but it's good that it actually shows in the result. There's like actually a connection between what we observe and what was intended when we designed the model. Okay, then what time is it? How much time do I have? 20 minutes. We do a little ablation. Should we train all of these heads sequentially or jointly? A big question in the concept space. We all know that training them sequentially is better to avoid leakage, and it actually helps us train in a more stable way. So we end up always training sequentially. However, the question of whether we should use a fixed alpha or learned alpha depends on the regimes you want to be using. Because if you have high levels of corrections available, you have a lot of expert time that's available to you, then you should probably use a learned alpha, because the model is able to transition to regimes where it relies a lot on the correction. And it really plays a role, like the alpha plays the role of an adaptability parameter between robustness and performance, and it can like help adapt. But when you go to lower regimes, the problem is that if you train the model with a lot of corrections and you actually apply it's the other way. If you train the model with low corrections, but you apply a lot of correction at the query, you end up with a mismatch between the distribution of the query and the gallery, and the alpha will adapt too much to this regime in the gallery. So you want to be using a fixed alpha in that kind of cases, so that you can always rely. Basically, a fixed alpha makes sure that the information of the appearance embedding, the visual embeddings, are not lost, never forgotten, and you will never do worse than this like pure non-interpretable model. So it's always a trade-off. If you want to do really good, use a trainable alpha. If you want to have the safety net of like worst case scenario, I do as well as like a non-interpretable model, you should use a fixed alpha, which is interesting because we have a design choice that can help ecologists adapt to their actual deployment scenarios. This is what our Disneys look like when you study the aesthetic embedding space, and it's kind of cool because you can slowly see the space cluster when you apply more and more correction in the concept space. And I think there's something interesting here, which is that because the problem, because you have a lot of problems where you have to think about AI and expert collaboration, but often this reflection is thought for at the label stage, like which of the predictions should you check here. The problem is that the problem of your identification is so hard that you can ask an expert to spend 3 hours on the image, he will still not be able to identify them robustly. So this question, we end up being able to improve our label performance, label space performance, our prediction space performance by supervising on the concept space. And I think it's something interesting because I don't know what other problems it could be applied to, but I think there's it's some way we dissect the problem to smaller problems, and we can use the expertise in these easier problems so that we actually solve problems that were not easy to do before. Okay. So the question now is, geometrically, how does it work? Why does it cluster like this? Is it because you add additional information? So we tried to explore this Disney space, and we looked at you have a question,
Yes,
Aya?
So I don't know if you did this ablation or if you're going to tell it, if we don't do the cropping with the ears, does it affect a lot?
Yeah, you divide your performance by 10.
By 10? So it's so the ear is huge in a sense.
Yeah.
Okay. Interesting. Okay, thank you.
So we dissect this Disney space, and we looked at it. So here on the right, on the top right, the points are colored by their identity, and you see that we have 2 different blue clusters that correspond both to the same identity, but this elephant there was an ambiguity. He was encoded by 2 different SEEK codes, which makes sense because here on the bottom left you can see its left ear, but on the bottom middle you actually can't see any ears. So the SEEK codes are different. So you have 2 clusters and 1 elephant, but still it's close enough that it's able to make the connection and be retrieved together using a KNN. Well, on the bottom right, you see that you have an elephant that has the same exact SEEK code as another elephant. So you have same SEEK code but different ID. And we see that our hypothesis is that you have a grounding that happens by SEEK codes, and basically the information is used to make a course level organization of the embedding space. And at a final level, the appearance head, the mega descriptor, the swing transformer, is actually helping to connect and disambiguate these cases, these two kind of ambiguities. So you end up with cases where here you have 2 different SEEK codes, but using visual information, basically the model was able to say that these 2 are different because their butts look different, right? And the shape of the butt is not an information that was contained in SEEK codes. So I think it's an interesting dissection to show how these 2 different heads, the concept head and the visual head, interact. Okay, and yeah, actually I showed you this. So we try to go a bit to understand which of the concepts are helping the most. And this is well obtained. I already presented this. And yeah, one last note. I think it's important to say that these elephants are very endangered, and in some way by doing this AI work on them and by representing them just by these SEEK codes and these biometric things, there's a little risk of doing reductionism, because you reduce them basically to a vector in an embedding space. But also there are many different ways to recognize their identities, and I don't know, I feel like we're doing AI, we should not forget that what matters in the end is the well-being of these elephants, and try to understand how to do better conservation. And although they represent a very, very interesting deep learning problem, we should always think about our models in a way that's actually in a downstream way thought for the conservation of these elephants. So if you have any questions, Veba and I are very happy to answer them. Yeah. Yes, Patrick? Did you have a question, Patrick?
Patrick, I think you're muted, maybe. You can't hear you for some reason.
Oh, sorry, I selected the wrong microphone.
There you go.
Okay, great. So first of all, thanks for the nice presentation. My question is for out of distribution, namely, would this approach also work for Thai elephants? Because I just know from my vacation that Thai elephants have different characteristics, like the thing behind the head. So would this actually also work, or would you need to change the concepts? Like,
I have no clue. I haven't tried. We don't have a data set of Asian elephants. I think by intuition, I'm not an ecologist, but by intuition, I would say the concepts would still work. I know, for example, for African savanna elephants, because they're in the forest, instead of having their hair like completely perpendicular, they tend to have their hair folded a bit back. So it's harder usually to see the little details on the ears because of the angle, if you're not in the right angle. So honestly, I cannot answer, sorry.
okay, but still thanks. Just out of curiosity.
Yeah. Do you have a question, Pietro?
Yeah, thank you for the presentation, Antoine. I'm wondering, like, how is the inference information collected? Like, are they actual pictures from a camera that is periodically collecting pictures of elephants? Is there is it possible to have a video of the elephants and the camera following the elephant, like, and you're just capturing frames from the video? How does it work?
So the way this data is collected is that it's rangers that almost every day go in the field and have a Land Rover, and they drive in the field and they actually try to look for elephants, which is something that matters, because in ecology, sometimes you want to have very systematic things where you're going to stay somewhere and you look around you and you see what's around you. Oh, actually, there's nothing, and it is an information, right? But here it's biased. Like, they are looking for the elephants and they try to take pictures of them. And usually they use the jeep to try to go on the other side to have also the information of the other ear. So the photos that are in the current data set are photos taken with a DSLR, usually with a long lens, and taken from a car. But I know there are a few camera trap photos also that ended up in the data set, and the photos are still performing as well. So I think it would be very different if, for example, we had photos from the top, like drone photos, but I don't think there's too much bias for, like, the camera is too much, like, so much bias in the model. But yeah, we could definitely think about using using video and trying to extract frames from it. But I think making re-identification, really using the information of the video, would be a bit harder.
But what I meant is, like, at least for the pictures that you want to label once you have trained the model. So imagine you have a trained model and experts that want to label new videos or new pictures of elephants. Like, if you had if the rangers find the elephants and take pictures consistently of the same elephant from different point of views, at least you would have information of both sides of the elephant. Like, I'm not, like, I don't know whether, like, this kind of information might be available in practice.
Yeah, so in practice, they keep looking for the monitoring is still ongoing. And in the data, what we do is that we use data from 3 years and we split the data to have a gallery and a query for evaluation. So technically, it's old data from the past, and we pretend some of it is like new data and some of it is old data. But what we're going to do right now to finish the paper is that we're actually deploying a user interface, a tool that they will actually use to re-identify a population that will not be used before. So we'll have a user study with like one user, but the idea is to try to see if it actually works in a current scenario for new images that are still not even taken.
I see.
Yeah, I'm sorry. I'm not sure if I actually answered your question.
Yep.
You have. Okay. Who raised their hand first? Okay. Oh yeah, Natalie, you had a question for a long time. Sorry.
I guess I'm next. Thank you. It was very interesting, especially to learn about elephants and how to encode them. I didn't want to interrupt in the middle of the presentation. I was more curious about the baseline that you compared. If you can elaborate a bit more about it.
Yes. So I compare it against two baselines. The first one is Mega Descriptor. It's a swing transformer that's pre-trained on a data set called the, oh my God, I forgot. It's like a data set for re-identification with about 100 species. And the other one is MuID, and MuID is, wait, let me look up who did that. I forgot the name of their organization. Oh my God. Yeah, MuID was done by Conservation Labs, which is a nonprofit that deploys tools for ecologists, and they have a lot of private data of these of different species. So they pre-train on this private data, and actually we reach similar results. And it's much below what we obtain when we actually crop the ears with architecture. And I think architecture-wise, both of them are swing transformers. And I also think, I haven't tried Dino. I mean, I have tried Dino a long time, but not in a very, like, just, you know, in a very vibe codey way, not in a very systematic experiment way. And I don't think the performance are so much better. I think for this problem, this is my intuition, I think we're really in problems where the core of the problem is the data, and how do you incorporate everything together and not actually the architecture. I think these architectures are all very performant at extracting geometric and visual information from the models. This is my understanding. Would you agree, Vaibhav?
I'm not an expert in a multimodal, but I was just curious about VLMs. Text with visual language, large language models, and like few shot learning. What if you'll give them prompt that described several examples? And I was really curious to understand just what their status compared to the dedicated. It seems like the transformer that you shared was dedicated to those tasks.
Yeah.
Okay.
For ReID, I haven't tried, but I'm pretty convinced it would not work, but maybe I'm being pessimistic. However, it's been shown recently.
Maybe I can take this. Yeah, okay. So like
okay,
this is actually a question.
Vaibhav?
Yeah, this is actually a question I also got when I was presenting this for my PhD candidate thing 2 years ago. And back then I tried some VLMs and it did not work well. For a lot of reasons. I think, okay, VLMs have increased, VLMs have improved since then. But from what I've understood, VLMs are they're not very discriminative among them. So when you give a lot of examples, they can try to come up with something, but they're not so much discriminative that you can re-identify between two different elephants. And part of the other motivation is I think we'd want to be operating within a single GPU constraint in inference time. A lot of these VLMs feel like an overkill for the problem we have, because we have very well identified concept space, we have very well identified image space. So adding in an additional modality of text would just make it, at least for our problem, it would make it unnecessarily complicated. And also we'd have to think about more than single GPU, or like a bigger GPU kind of setup. And in the operating space of deployment, this is about our couple million is about the best we can do in terms of deployment. So I think a lot of these reasons is why we never considered VLMs. But yeah, at least from 2 years ago, the VLMs are not even good enough to identify between two different elephants. They mostly call it elephant. Like it's hard for them to discriminate elephant A versus elephant B.
Yeah.
Thanks.
I also think that there's a challenge with data, because here like the private set, the data set we evaluate on is private, and I think it's probably one of the biggest data set that exists on there. I think there are less than 200,000 images labeled, like all over the world, like all data sets combined, probably. And so you need to think about like models that are not too hungry for data. I think multimodality would create a lot of challenges in alignment that would require a lot of data. Like we have to think data constraint.
Okay, thank you.
Do you have a question, Divish?
Yes. So human face identification was actually, you can make a very, very good amount of progress with just like a traditional PCA transform and just grouping images. What exactly is it about elephant identification that's so different from human face identification that makes it so difficult?
I think it's the amount of data. I like, for sure, for us, all elephants look the same because it's not our job to distinguish elephants. I'm sure if we would do it every day, probably we could differentiate elephants more easily. But for AI models, I think the problem is data. With like, I think these face recognition models rely on a huge amount of data, right? Like, this is my understanding, but.
And also, human data is very clean. If you think about it, humans have a very structured way of taking photographs. You can take passport-sized photos and just scale it to millions, and you get you get enough data that even simple techniques would work. Elephant data is very sparse, and they're taken from DSLRs, and they're taken often from sometimes moving vehicles. So it's not as clean as we'd expect from human intuition. And most humans can discriminate other humans with very less time. Even experts would take a lot of time, as Antoine was mentioning during the presentation, to discriminate between elephants. So that in itself is a skill. And on top of that, it's sparse data. So we'd have to rely on clever techniques and like clever architectures and all of these sorts of bells and whistles, which in an ideal world, we don't want to rely on that. But the fact that we have to compensate with something for lack of data is through architectures and clever work like what Antoine presented. Like I hope that makes. That gives at least our intuition on the difference.
Right, that does make sense.
Yeah.
I also had a second small question. Since you seem to have data for a decent amount of data for individual elephants, could a 3D reconstruction type approach actually be used to generate a lot more synthetic data per elephant?
Yeah, technically it's stuff that we could think about. And there's someone in my lab called Julia that has worked a lot on generating ecological data. The problem with ecological data is that the distribution is very different from the rest of data sets we find on like in classical deep learning and we see in conferences. And yeah, it's hard to stick to things that are actually species and very easy to invent and mix stuff together. And I'm not a pro on generative AI, but I know that she found a lot of challenges doing it. But I think it's interesting. But how would we generate a new identity that's also variable and consistent across images in a way that's like natural, like elephants change a little bit, but they don't change too much. Like, how will we model that? I don't think it's necessarily so easy.
Thank you.
I mean, that would be an interesting question, honestly. A tough one though. Yeah, question, Matthew.
Yeah. Obviously, thank you so much for the talk, guys. That was really fun, really interesting. I do have a question on like the alpha, the mixing coefficient between the two representations. So the ablation experiments that you had, I'm guessing those where you retrain the model with different alphas and you plot a point with the retraining, right? do you see an instance where it could be useful to intervene on the alpha coefficient at test time? So you change that test time. And then the intuition behind this, I can see an example, for example, where an expert cannot come up with a SEEK code because the ears are occluded, and he realizes that that representation should probably be avoided for re-identification. So they can go ahead and change that alpha to 0, or whatever it is that is, I don't know if it's 1 or 0, whatever it is that you make the SEEK code based representation to not take much weight. And then take that extra step forward, you can even think of it as a bit of the alpha as a bit of a certainty of how certain the expert when intervenes are on their SEEK code that they just generated, right? So you could play around with intervening on that as well. That's what I was wondering if you had experience that or you thought about that.
I think Vaibhav, you should answer because I know you have takes on this.
Yeah. So by default, we don't force correction. So if you choose not to correct, we just take it's like a pass through almost, and it works it works better than the baseline. So it has more. We do incentivize that even if you don't correct, we have a better gain in performance. But I definitely see alpha. I mean, we can't guarantee things again. There's only so much we can do at test time. So I definitely see a lot of value proposition and correcting alpha and just like playing around, because again, human intuition is a very nice thing and a tricky thing at the same time. So imagine giving a couple of knobs to set to alphas where you get a slightly diverse mixture, and then try to see if you can identify from what you see on your screen from the diversity that you spotted the right elephant. So yeah, I definitely see it. We haven't done it, but I guess that's the whole point of the N=1 human study Antoine is talking about, is like, what other things can we do that we can't think outright from just being deep learning people and having virtually zero experience with elephant in the field. So yeah, that's a whole thing Antoine is focusing on.
No, nice. Yeah, very good work. Thank you.
Yeah, you have a question, Aya, and I think we should maybe keep it here because we'll go too much over time.
Yeah. Thank you so much for the talk. I'll
No, let's have your last question.
Oh, okay.
Sorry.
I think Matteo asked this question during the talk, but I didn't get the answer that much. So in the architecture, basically you have like a black box route and a concept route where you have probes and you predict the concept. But then you have like this expert that can change the output, and then you basically project the embedding and add them together with an alpha coefficient, and that's the output. So during training, the expert correction is done by the ground truth, right? Like, that's my understanding. Okay, so basically during training, it is just like as if you're doing like sequential training, or sequential training in a sense with a probability. That's kind of like my understanding. Okay, so then so when you were comparing sequential training versus joint training, so basically the joint training did not have the correction at all?
No, the joint training would have the corrections. It's just joint training means that, you have your two branches. You have the appearance branch and you have the projection branch. Let's assume that you already trained your concept head that predicts the concepts. Your concepts are already partially corrected, and you have these two branches, a visual and projection, and then you sum them. It's these two. Do we train them together with a loss only on the sum of them, or do we train them first the appearance branch with a loss on this, and then we train the projector with two? So like the second scenario, sequential, basically only teaches the projector to sum on top of the already trained appearance and color.
Okay, so but in both cases, you basically flip based on the ground truth.
Yes, exactly.
Okay. That's my question. Okay, thank you so much for the talk.
No, thank you so much. Thank you very much for the invitation. It was very fun. I'm always happy to share more. And if you guys have any questions, if you want to start interpretability project in the field of ecology, I'm always happy to collaborate. So thank you very much for the invitation, and shout out to Vaibhav, who's been supporting me for almost 2 years now.
Thank you so much, Antoine and Vaibhav. We really appreciated this. This was fantastic. And yeah, well, thank you so much, everyone, for joining us. We'll have another talk next week as well. I think it's going to be Maria Martinez. Yeah. So if you're around, please come by. Otherwise, hopefully, we'll see you all very soon. Right.
Goodbye.
Thank you.
Bye.
Having fun. Like.
Thank you, Matteo.